Laboratory 3 deals with isotopes and mass spectrometry. First, let's talk about isotopes and define the term. An isotope basically is the same element, but with a different number of neutrons. Neutrons being the key discriminatory subatomic particle that discriminates one isotope from another. So as an example of isotopes, we can look at strontium. Strontium actually, if you look at the periodic table, is in group 2 of the periodic table, and there is strontium right here. Okay. You notice that you have a number here that is 38. So as you remember from the lecture on the periodic table, 38 and all of these numbers that are usually on the top of the periodic table, it depends on the type of periodic table and how they organize it, but this top number or the main number is actually invariant, and that number represents the number of protons. So the number of protons in strontium is defined by 38, just like the number of protons in calcium is defined by 20, or the number of protons in cesium is defined by 55. So that's 38, which is the number of protons in strontium. The atomic number, or the number of protons, is invariant. So strontium actually has 5 isotopes. Those isotopes are strontium-38, which is the atomic number, and one of its isotopes is 84. There's another isotope of strontium. It still has the atomic number 38, which is the number of protons, but in this case, we have an isotope that's 86, so strontium-86. And then we have strontium, still going to be 38 because that 38 defines the element strontium. We have a strontium-87, and then we have a strontium-88. So there's actually 4 isotopes of strontium. I may have misspoke when I said there is 5. So strontium actually exists in 4 forms. Now what's the difference between form 1 of the element versus form 2 of the element versus form 3 and form 4? Well, the difference really goes down to the heart of what is an isotope, and the difference is the number of neutrons. So this also has a natural abundance. So the natural abundance is how much of that particular element or that particular isotope of that element exists in nature. So this is a table that you can just look up. We don't really calculate these. The natural abundance for a particular element is given to us. And so the natural abundance of the strontium-84 isotope is going to be 0.56. The natural abundance of the 86 isotope of strontium is 9.86. So we can actually represent these as a percentage. The 87 isotope of strontium is at a natural abundance of 7%. And finally, strontium-88 will have a natural abundance of 82.58%. So most of the strontium that we find in nature will be the strontium-88 form. And you can actually see here, if you look at strontium and look at its atomic weight, it is actually an average of all those isotopes. So 87.62 is very close to 88, and that's because the 88 form is present at 82.5%, while the rest of the contribution towards this molecular weight of strontium, the rest of this contribution comes in the form of 7% strontium-87, 9.86% strontium-86, and very little of that contribution comes from 0.56% strontium-84. So if you add up all these numbers, you actually will get 100%. So like that, strontium has 4 isotopes, neon has 3 isotopes, and almost every element in the periodic table has different isotopes. Carbon is very famous in that it has carbon-13 isotope, and then the carbon-12 isotope, which is the most naturally abundant form of carbon that's found on planet Earth. So that is essentially what isotope is, along with its corresponding natural abundance. All of this and this and this and this goes towards the molecular weight of strontium that you read in the periodic table. Henceforth, that number known as the atomic mass, is actually a weighted average of all these presences, or of all these states of the strontium isotope. So in this lab, you will actually determine isotopic abundance of different elements, as well as the isotopic abundance of different types of chemicals. Another topic that we really should talk about, but we won't, is a mass spec or a mass spectrometer. These instruments can run in the range of $500,000 to $1 million or even more. And what they do is they fragment the analyte. And by analyte means your sample that you put into the mass spec. You usually inject the sample, and then via injection, the sample gets bombarded with electrons, and then those electrons create fragments. So what you actually see in a mass spec is a mass over charge peak. M over charge, and I'm going to abbreviate that charge as Z, a mass charge ratio to be exact. So you can read the lab, and that will go into more detail of the type of technology and the magnetic plates and the electric fields that cause these fragments of the sample. In this case, the sample is going to be mercury. The mercury will be fragmented, in this case, into 1, 2, 3, 4, 5, 6 different fragments. So how many isotopes of mercury are there? Because that's what you injected into your mass spec instrument. Well, the answer is 6, because you have 6 fragments. So in this lab, you're going to determine the abundance of each of these isotopes. Notice in my x-axis, I have the term mass number, which is the number of protons. In my x-axis, I have the mass number, which is the number of protons. And then on my y-axis, I have the relative intensity. So what has the most relative intensity in the mass spec of mercury? The answer is this one. Okay, mass number 202 has the highest relative intensity. So we would expect mass number 202 of mercury to have its highest natural abundance. That is to say, the mass spec of mercury, or that atomic mass of mercury, will be most abundant in the 202 isotope. So let's analyze the mass spec of mercury, and you'll be doing this for several types of compounds for this lab. So the first thing you want to do is realize that the height of each of these peaks is representative of the amount of that particular isotope. So if you would take the area underneath this peak, that would be the amount of mercury 202. If you were to take the area under this peak, that would be the amount of mercury 198. So the first thing we would do is actually measure the peak height of each of these peaks. I can make a column here and call it peak height. I can make another column on the left of it and call it mass number. And then here I'll have a third column, and I'll call that the fractional abundance. And then my fourth and final column in this table would be my weighted abundance. So I'll have my mass number, my peak height, which is the measurement of that height of that peak, its fractional abundance, and then the weighted abundance. So let's first of all put our mass numbers in. So here's mass number 198, the peak height of 198. Now you can measure this in centimeters or millimeters. It does not matter the units. So you can measure this in centimeters, millimeters. The units of measurement doesn't really matter. So when I measure that peak height, I get a peak height of around 2.2, maybe 2.3. I'll call it 2.3 centimeters. So the peak height of that 198 isotope is 2.3 centimeters. The peak height of my next isotope is mass number 199. The peak height of 199 will be around 3.6, maybe 3.7. So I'll go with 3.7 centimeters. Mass number 200 will have a peak height of around 5 or 5.1 centimeters. So mass number 201 will have a peak height of 2.9 maybe, or 3 centimeters. And we have 202 and 204 that's left. Mass number 202 has peak height of about 6.5 or 6.6 centimeters. And finally, mass number 204 will have a peak height of about 1.5 centimeters. So now I have my peak height. Each of the isotopes of mercury have their corresponding mass number, which is the number of protons plus neutrons. The mass number is the number of protons and neutrons. So now I'll determine the fractional abundance. Notice here that mercury, the element of mercury, has 1, 2, 3, 4, 5, 6 isotopes. The number of protons in mercury is always going to stay the same because that's invariant. That's going to be at 80. The number of protons will be 80. The number of neutrons is going to be 198 minus 80 because mass number is protons plus neutrons. I know the number of protons in mercury will always be 80. That is invariant. The number of neutrons in this isotope will be 199 minus 80. 100 minus 80 for this third isotope. 201 minus 80 for this isotope, and on we go. So that's the contribution of each of these isotopes. It's this element mercury. All of those are going to contribute to that 200.59 atomic weight that you see here in the periodic table. Remember, this number is a weighted average of all of these isotopes based upon their abundances in their mass spec. So now we will do the fractional abundance. In order to do that, we will take 2.3 divided by the sum of all of the peak heights. So if we look at 198 mass number, it has, as we measured before, a peak height of 2.3 centimeters. Well, what does that peak height contribute relative to all these other peak heights? In order to figure that out, you will do 2.3 divided by all the sums of all the peak heights. So when you do that, you'll get a value of all the peaks, which represent my mass charge ratio of all those fragments. And 2.3 divided by 22.2 is going to equal 0.10. If I multiply that by 100, that's essentially 10% or 10.4%. So the 198 fractional abundance relative to all the other mass charge isotopic peaks is 0.10. So I'll just put 0.10. I may include the third decimal place, 0.104. So like that, I'll complete the table. After I've completed this table, by determining the fractional abundance, the part over whole, or the contribution of each of these peak heights to the total amount of isotopes in the element of mercury, after I figured out their proportional abundance, I need the weighted abundance. So in order to get that, I will take the fractional abundance, that is how much that existed in the mass spec, times its mass number, which is the number of protons plus neutrons. So multiplying 198 times 0.104 is going to be 20.59. So we'll just call it 20.6. And that 20.6 represents the weighted abundance of isotope 198 of mercury. Likewise, the contribution or the weighted abundance of 199 isotope, which is protons plus neutrons, remember that's what the mass number represents, that is its definition, will be 199 times 0.167, 33.23. And like that, I will complete this table. Now that I've completed this table, determining not only the fractional abundance of my peaks in that mass spec, but I've also determined its proportion relative to its mass, protons plus neutrons, I've completed the weighted abundance. And all I have to do now is add these up, because remember, this represents a proportional abundance. By adding this up, I will get the mass of all 6 isotopes of mercury. So the addition of 20.60 plus 33.23 plus 46 plus 28.14 plus 60 plus 13.79 gives me an average atomic weight for mercury in all of its 6 forms, its 6 isotopes, of 201.76 AMU. AMU stands for atomic mass units. Some people also, if we study the mole, can also say it's 201.76 grams per mole as well. But we'll stick to this definition with regards to mass spec, because we're not really talking about the mole here. We're talking about isotopes, and the isotopes have to do with the atoms of mercury rather than the amount of mercury. So 201.76 is the atomic mass unit, the average weight of mercury. Let's check that with what we see, or our value in the periodic table. And the value in the periodic table is 200.59. Okay? 200.59, and we calculated a value of 201.76. So we are not that off. 201.76 versus 200.59 is a pretty good margin of error. It's probably less than 1% error if you calculate the error. It tells you several things. Number one, it tells you that mercury, when you put pure mercury or inject pure mercury into a mass spectrometer, you're going to get a mass fragmentation pattern that has 6 peaks representative of 6 isotopes. Determine the peak area and multiply the peak area by its proportional abundance, or you get the proportional abundance of the peak area relative to all the other peaks, and multiply that by the mass number to get the amount of mercury that's 198. This is the amount of mercury that's 199. This is the amount of mercury that's 200. This is the amount of mercury of 204. All of those come together to give you the 100.59 that you see in the periodic table. So that is the lab that you'll be performing for lab 3. You're going to construct a table. Now, one thing, this is pure mercury, which we know has the elemental symbol of Hg. What about something that has more than one atom? Okay, so such as HCl. Okay, you're going to have to identify the peaks of HCl. Look at your mass number. Mass number is protons plus neutrons. So this is 35 protons plus neutrons. This is 36 protons plus neutrons. This is 37 protons plus neutrons. This is 38 protons plus neutrons. What is your sample? Okay, your sample is HCl. So when you put HCl into a mass spectrometer and get its mass spec or mass spectrum, what's going to happen? Well, the first thing that you should know about mass spec is that it fragments it. So the molecule gets fragmented. Here, mercury gets fragmented into its individual isotopes that compose it. Here, HCl, hydrogen chloride, or hydrochloric acid, if you're specific, that also gets fragmented. But what will it get fragmented to? Okay, it's going to get fragmented into H and Cl. H has its own isotope, and Cl has its own isotope. Shown here is only one isotope of H, because Cl actually has 2 isotopes. H has 2 isotopes too, that's hydrogen and deuterium, but what's only shown here is the one isotope of H. Now, having stated that, can you guess the identity of each of these peaks? One of them is 35. What do you think 36 would be? What do we know about hydrogen? Hydrogen has an atomic weight of 1. Its atomic number is 1. So it's H1. We're not going to worry about H2 or radioactive H3 because only one isotope of hydrogen is shown here. So knowing that H has a mass number of 1, what do you think this peak is, the 36 peak? 36 peak, you would be right if you stated it is hydrogen and 35 Cl. What would this peak be? It would just be 35 Cl. And what's this peak? If this is 37 and this is 38, what is the 37 and what's the 38 peak? The 37 peak will be 7 Cl. What's the 38 peak? Hydrogen is 1. So the 38 mass number peak represents 1 hydrogen, the isotope of hydrogen, and 37 Cl. So that's the power of mass spec. It can actually resolve individual isotopes. So if you buy hydrogen chloride from the store, or I guess hydrochloric acid from the chemical company, you're getting hydrochloric acid that is 37 Cl and 1H. You're also getting hydrochloric acid that's 1H and 35 Cl. You're also getting a little bit of, so this is not really pure if you think about it, depends on what grade of hydrogen chloride you're talking about. You'll also get some 37 Cl isotope, so that's an impurity. You'll also get some 35 Cl in your hydrochloric acid or hydrogen chloride. That's an impurity. And I think I told you this before, but hydrogen actually exists as also deuterium and radioactive tritium. But this is radioactive, so probably this will decay. You'll probably get some of this in that hydrogen chloride bottle. You'll get some of this alone in the hydrogen chloride bottle. Okay? Hydrogen that's without a chlorine partner. So hydrogen chloride, its mass spec is pretty complicated, and it's not really hydrogen chloride. Okay? You have hydrogen chloride with this chlorine isotope, you have hydrogen chloride with this chlorine isotope. It all depends on their, if you go back to your mercury example, their peak heights and the fractional abundances. So you will make a table just like you did for mercury with hydrogen chloride. You'll make this exact same table, and you will look and measure at the proportional abundances of the fragments in hydrogen chloride. You'll also do it for bromine. You'll do it for a whole litany of small molecules to determine their isotopic abundances, and also being able to identify these peaks. Identifying the mass spec peaks is very, very powerful, especially if you're looking at a clinical sample or an unknown sample. So don't forget to do your pre-lab and your post-lab. Put that into your lab reports, and this is a lab that really shows the power of mass spectroscopy, a very powerful instrument, very expensive instrument. Do take a look at some of the mass specs in the literature or on the web if you're further interested in this topic. Thank you.